Hello everyone, welcome to this channel. I'm from SCIE Algorithm Programming Club and I'm Jimmy. And today I'm going to talk about time and space complexity. So what are time and space complexities? Space and time complexities are two aspects of how we analyze the efficiency of a code or algorithm. Time complexity is how the running time of the algorithm grows with the size of the input. Space complexity is how the memory an algorithm uses grows relative to the size of the input. So how do we measure this? Well, we use the big O notation. So the big O notation is how we express the time and space complexities in. It describes the upper bound of growth, or the worst case scenario, where the n represents the input size. So we can see that for O1, it stays constant as the data input increases, the time, which is the time usage, doesn't change. While for ON, as data input increases, the time will increase linearly. While for ON squared, when the data input increases, the time will increase by squared. So why is time and space complexities important? Since it measures the efficiency of the algorithm, a lower time and space complexity could reduce the time spent on calculation, the need for larger memories, and etc. This means that it could reduce costs and increase user experience for applications and more. Let's take an example of a computer game where if we increase the space complexity, it will be really laggy and you will have a high input lag. And also, if it has a high space complexity, our RAM might exceed and it will slow down the program also. So in competitions like USACO, there are limits to the time and memory usage and the size of the input given, meaning we need to keep the time and space complexities in mind. So here's a visualization of the input size and how they increase in calculations. So we can see that for ON squared, as the input size increases, no matter if it's time or space, it will increase dramatically. For ON, it only increases by a little, and for O1, it doesn't change. So this shows that how many calculations or how much memory we're using. So we can see that it's better to keep those factors down. So firstly, let's talk about time complexity. So what is time complexity? Time complexity means how efficiently an algorithm runs as the input size increases. Time complexity is important as an algorithm with lower time complexity will run faster since it will do fewer basic calculations. So how do we calculate time complexity? Time complexity could be seen through how much the program scales according to the input. We normally take the highest power as the time complexity. One of the easiest ways of calculating time complexity is seeing the highest number of loops nested together. So for example, a bubble sort will be ON squared since there is two loops, with one nested in the other. A linear search, on the other hand, which will search through a list, it will be ON, since the amount of numbers searched scales linearly with the increase of the size of the input. So there are also other ways where we see how to calculate the time complexity, which is the log n. So one of this is binary search, which eliminates half the list with every comparison, so making it O log n. Remember here that the log is in base 2. So another example is quicksort, which the step of putting numbers smaller than the pivot to the left and numbers larger to the right is just basically going through the whole input. So it's going to be ON. And splitting the array into roughly halves will be O log n. So the time complexity of the whole program will be ON log n. Another example is searching a number in a tree. So let's talk about space complexities now. So what is space complexity? Similar to time complexity, space complexities measures the use of memory an algorithm needs to run based on the size of the input. Space complexity is important because every device has limited memory. If an algorithm uses too much space, the program will be slowed down and even crash. So how do we calculate space complexity? If an algorithm uses one variable, it will take up one space. So there is a limit number of variables. So it will be O1. However, if there is an array that scales linearly to the input, then it is On, and so on. For example, when finding the shortest path in a graph, we will have a matrix that stores all the distances between all pairs of matrices. Since we have n vertices, then the space complexity will be On squared. So here's an example of a simple find algorithm of finding a number in an array. We can see that there's only one for loop, so the time complexity will be On. And since there was only a limited number of variables created and not for every input, so this will be O1 space for space complexity. And for this example 2 of creating a matrix, you can see there's two for loops to go through and creating a 0 for each spot. So this will be On squared for time complexity. And for space complexity, it is also On squared, since the input is size n, and we're doing a squared of that. So it's n times n, and we're making that much variables in the matrix or the array. So let's have the summary. So the time complexity is how fast an algorithm runs as data grows. Space complexity is how much memory it consumes. And big O helps us compare algorithms quickly. So that's all. Thanks for listening.